Welcome you in the lecture series of random processes, detection and estimation. Before to start this series, let me introduce myself. I am Parvendra Kumar, Assistant Professor in Thapar Institute of Engineering and Technology in Electronics and Communication Engineering Department. I did my PhD from Indian Institute of Technology in Optical Communication. My research interest area is quantum optical communication and Li-Fi technology. This series gives you an overview and introduction to signal detection and estimation. Before to study detection and estimation, we require a good knowledge of the fundamentals of probability, random variables and random processes. Also the good knowledge of linear algebra. The course contents have 7 different outlines. A background, where we will look out the review of random processes, Gaussian variables and process, problem formulation and objective of signal detection and signal parameter estimation. The second outline is the statistical decision theory. In the third outline, we will discuss detection of deterministic signal, and in the fourth, we will discuss about detection of random signals, and in the fifth outline we will discuss about non-parametric detection, and after this we will discuss about estimation of signal parameters and signal estimation in discrete time. And in the objective of this lecture, you will able to explain why detection and estimation is necessary, how detection and estimation is done, and also you will able to explain how linear filtering is used for parameter estimation, and you will also able to explain the use of classical and Bayesian approaches to formulate and solve problems for parameter estimation and signal detection for noisy signals, and the difference between the linear filtering methods for parameter estimation and signal smoothing. And also you will able to analyze discrete time approach for signal estimation. There are some textbook and reference books. In the textbook you can follow the H1 tree, detection, estimation and modulation theory, John Valley and Sons publication, and it is published in 2001. And there are 5 reference books. And in these reference books, I will follow reference book number 4 and 5th, SMK, Fundamentals of Statistical Signal Processing, Estimation Theory, in 1993, and fifth one is the SMK, Fundamentals of Statistical Signal Processing, Detection Theory, and in 1998. Now we start with the introduction of probability theory. Initially 2 questions should come in your mind. What probability and why probability? Now I will try to give you answer of these 2 questions. Probability theory gives a mathematical framework that allow us to make uncertain statements. So the probability theory is applicable in a situation where uncertainty exists. Uncertain statements means that are not deterministic, or there is no absolute certainty about the statement. For example, the prediction of weather tomorrow, or recovery of the transmitted signal from the received signal. Now to better understand the probability, let us take one example. If I say that the chance of coming rain tomorrow is 40%, then the probability of coming rain tomorrow is 0.4. So the chance of coming rain tomorrow 40%, I can represent it in the probability manner, like the probability of coming rain tomorrow is 0.4. So we can predict what may happen. We cannot exactly determine what may happen. Another example is the probability in a communication, where we try to recover a message signal from the received signal containing noise. Noise is the random fluctuation of the signal variables. So without the theory of what random means, we cannot understand what noise is. When we talk about the recovery of the message signal, we are basically talking about the estimating the original signal from the received signal. The randomness and estimation are the fundamentals of the probability theory. We use probability theory in artificial intelligence also in two different ways. Like it tells us how to design our algorithm in artificial intelligence, and also to theoretically analyze the behavior of the proposed artificial intelligence system. Machine learning also make heavy use of probability theory. It deals with uncertain quantities. So as far we know that the probability theory allows us to make uncertain statements. Now the question is how to quantify the amount of uncertainty, or how much amount of information in the uncertain statement. The answer is information theory tells us about amount of information in a message or statement. If there is a pen, you can see on your screen this is a pen, and after showing you this pen, if I will write a statement, it is a pen. So the probability of coming this sentence or this message is 1. So you can say there is no information for you because you know beforehand what is this. This is a pen, and so you can say the amount of information is 0 here, and there is no news for you. And surprisingly, if I will say that after showing you this pen, if I am saying it is radar, so the probability of coming this is very less, this message. And you can say the amount of information is more here, and there is news for you because you don't know this kind of a pen is a radar. So from this discussion, we can say that the information theory is related to the probability theory. So mathematically we can say that amount of information will be inversely proportional to the probability of that message. So I can say that amount of information in a message will be inversely proportional to the probability of that message, and I can write it mathematically as IM, amount of information, it is equal to log E2 1 by probability of that message. Now we come to the decision and estimation. In decision theory or detection theory, we have to make a decision on the basis of hypothesis testing, and we have to decide whether the signal is present or the signal is absent. And in estimation theory, we assume that the receiver has made a decision in favor of that the signal is present at the receiver, but some parameters associated with the signal may not be known. So the goal is to estimate those parameters in an optimal fashion based on finite number of samples of the signal. Now before to start the probability theory, we have to first explain some definitions such as random experiment, sample space, event, algebra of sets means set of operations, Venn diagram, identity matrix, different laws like commutative law, associative, distributive, De Morgan's law. And after these definition, we will able to define the probability in 3 different ways: relative frequency definition, classical definition, and axiomatic definition. So now first we will start with the random experiment. The process of any observation is termed as experiment, and the result of the observation is termed as the outcomes of the experiment. The experiment will be the random experiment if the outcome cannot be predicted. For example, rolling a dice, tossing a coin, drawing a card, selecting a message signal for transmission from several messages. Now sample space. The sample space, or sometimes known as the universal set, is the set of all possible outcomes of the random experiment, and it is denoted by S, and the element in S are the sample points. Each outcomes of the random experiment corresponds to the sample point. Let us take one example here. Find the sample space for the experiment of tossing a coin one time I am tossing a coin. So the sample space will be head or tail. So these are only two possible outcomes. So these outcomes, head or tails, are the sample points. So this means you can say the outcome of the random experiment corresponds to the sample points. And if I am tossing a coin two times, so what will be the sample space in this case? So the sample space will be head head, head tail, tail head, or tail tail. So these are also the sample points here. Now let us take another example. Find the sample space for the experiment of tossing a coin repeatedly and counting the number of tosses required until the first head appears. So what will be the sample space here? Sample space will be 1, 2, 3 and so on. So you can say that my head can become in the first toss or second or third and so on. So there are infinite number of outcomes in the sample space. Now we will discuss about event. The expected subset of a sample space is termed as event. Now, to understand the event, let us take one example. Consider the previous example, tossing a coin repeatedly. And let A is the event that the number of tosses required until the first head appear is even. What will be the event A? So you know the sample space of tossing a coin repeatedly until the first head appear, it is 1, 2, 3 and so on. So we are requiring the event A is the number of tosses required are even. So the event A will be corresponds to 2, 4, 6 means in second toss, in fourth toss and sixth toss and so on. So the events will having the even number of tosses required. And next point is let B is the event that the number of tosses required until the first head appear is odd. So now what will be the event B? So event B will be 1, 3, 5 and so on. And third point, let C is the event that the number of tosses required until the first head appear is less than 5. So what will be the event C? So here the number of tosses required will be less than 5. So the event C will be 1, 2, 3, 4. So and it is less than 5. Now we will use some notation in this series. If xi is an element of set S, then we can say that xi belongs to S, and this is notation for belongs to. And if xi is not element of S, then we can say that xi doesn't belongs to S, and this indicate not belongs to. And if A is subset of B, then we denote it as A subset of B, and this is the indication of subset. Now the fourth point is the algebra of sets, in which first we will discuss set operations. First point is equality of events. Two events A and B will be equal if they are having same elements or same sample points. So we can represent these as A is equal to B. Event A will be equal to event B if A is subset of B and B is subset of A. Another is complement of event. Let here A is subset of S, and the complement of event A contains all elements which are in S but not in A, and it is denoted by A bar, complement of event A bar, and it is the A bar will having the all sample points xi, such that the sample point xi belongs to S, and also the sample point xi doesn't belongs to A. Simultaneously it belongs to S and doesn't belongs to A. And this is for the such that. Now third point is union of events. Union of events A and B is the event that contains all sample points in either A or B. So it is A union B, union of event A and B. It will have the sample points and the sample points such that the sample point belongs to A or sample point belongs to B. Means it should belongs to A, either A or B or in both. Now fifth point is intersection of events. The intersection of events A and B contains all sample points which are in both A and B simultaneously. So A intersection B will having the sample points such that the sample points belongs to A and simultaneously the sample point belongs to B. Now fifth point is null event. The event which is not having any sample point is termed as null event. So and it is denoted by phi. So the phi will be equal to the complement of the universal set. Now fifth is the disjoint event. Two events A and B will be mutually exclusive or disjoint event if they contain no common sample points. Means if there is no common sample points, then A intersection B will be null set. Now the second point in algebra of sets is the Venn diagram. The Venn diagram is a graphical representation of the set operations like equality of events, complement of the event, union of event, intersection of events, null events and disjoint event, which we have discussed in the previous slides. So in the graphical representation, like if I am having this type of graphical representation, and this area represent the universal set S, and we are having this is event A and this is event B, this is event B. So the shaded region, it will be represented by A union B. Another, what will be the shaded region? Here you can see that shaded region is the common the sample points which are common in both A and B. So it will be A intersection B. In this you can see that the sample points here belongs to S but doesn't belongs to A. So you can say this will be complement of A bar. And another is here the sample point belongs to A but doesn't belongs to B, and here B is subset of A. So the sample points here in this shaded region, we can represent this as A intersection B bar. They doesn't belongs to B, and B bar means all the sample points that doesn't belongs to A. Now from these above figures or definitions which we have discussed previously, we have the following identities. S bar is the null set, so S bar will be equal to phi, and phi bar will be equal to universal set, and A bar it will be equal to event A, and universal set union A, it will be the universal set, and S intersection A, it will be equal to event A, and also A union A bar, it will be the universal set, and A intersection A bar, it will be the null set. The fourth point in the algebra of set is the different laws. First is the commutative law. Here A union B is equal to B union A, and A intersection B will be equal to A B intersection A. So we can interchange A and B with respect to this notation intersection and union. So this means you can say there is no order important. You can take first B and after this A, or A and B. And another is the associative law. According to this, A union B union C will be equal to A union B and union C. So here we can, and in this A intersection B intersection C will be equal to A intersection B intersection C. So I can take first A B intersection C or A intersection B. Another is the distributive law. According to this, A intersection B union C, it will be equal to A intersection B union A intersection C, and A union B intersection C, it will be A union B intersection A union C. So here the A intersection is distributed over B union C, and here A union is distributed over B intersection C. Another is the De Morgan's law. According to this, A union B whole bar, it will be equal to A bar intersection B bar, and A intersection B whole bar, it will be equal to A bar union B bar. So if I want to distribute this whole bar into individual event A and B, then I will change my my notation from union to intersection or intersection to union. This is De Morgan's law. Now let us take one example. Consider a random experiment of tossing a coin 3 times. Find the sample space if we wish to find the exact sequence of head and tails obtained. So the sample space will be head, 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 tail, head, tail, head, tail, head, head, and similarly head, tail, 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 head, tail, 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 head, and tail, tail, tail. So these are the total number of sample points, and number of sample points in the sample space are 8 here. Another point, find the sample space if we wish to find the number of heads in the 3 tosses. So means I have tossed the coin 3 times and I want to find out the number of heads in 3 tosses. So the sample space will be 0, 1, 2, 3, means here 0 means the head is not appears in any 3 tosses, and also you can say the 2 indicates that 2 heads were obtained in 3 tosses, and in the 3 means all 3 heads were obtained in 3 tosses. Let us take another example. An experiment of rolling a dice until 6 is obtained. Find the sample space if we are interested in all possibilities. So I am tossing a coin until 6 appears. So the sample space, it will be 6 or 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, or 1, 1, 6, 1, 2, 6, 1, 3, 6, and so on. And here this first row indicate that 6 is obtained in first throw, and this second line indicate that the 6 is obtained in the second throw, and 6 is obtained in the third throw and fourth throw, and so on. So these are the all possibilities. And part B, find the sample space if we are interested in the number of throws needed to get 6. So here the sample space will be 1, 2, 3, 4, and so on. So I can get the 6 in first or second or third and fourth and so on. So in standard form I can write it as the sample points such that the sample point belongs to the set of natural number. Set of natural number means 1, 2, 3, 4, and so on. So this is the set of natural numbers here. Let us take one example. Consider the switching network as in figure. Let A1, A2, A3 denotes the events that the switches S1, S2, S3 are closed. Let AB denotes the event that there is a closed path between terminal A and B. Express A in terms of A1, A2, A3 for each of these networks. So for the first circuit AB, it will be equal to A intersection A1 intersection A2 intersection A2. This means the circuit at point A and point B, it will be closed. If the switch S1 is closed, means event A. Switch S2 is closed, means event B. And switch S3 is closed, means event 3. And these three switches should be closed simultaneously to maintain a closed path between A and B. So AB, it will be A1 intersection A2 intersection A3. So similarly for the part B, AAB, it will be A1 intersection A2 union A3, and from the distributive law you can write it as A1 intersection A2 union A1 intersection A3. This means this or this S1 or S2 should be closed, or S1 or S3 should be closed here to make a closed path between A and B. And for the part 3C, it will be AAB, it will be A1 union A2 union A3. So this means for making the closed path between point A and B, there should be S1 should be closed, or S2 should be closed, or S3 should be closed. Either. So this means from of these three switch, either switch should be closed to make a closed path between A and B. And in the fourth part, AAB, it will be A1 intersection A2 union A3. Now let us take one other example. Let the experiment of rolling two dice find the sample space. So if I am rolling two dice, the sample space, it will be 1, 1. The outcome in the first die and outcome in the second dice. Outcome in the first dice and outcome in the second dice. So for the first row, the outcome is 1, 1, 1, 2, 1, 3, 1, 6. And for the in the second row, it is 2, 1, 2, 2, 2, 3 up to 2, 6. And in the sixth, it will be 6, 1, 6, 2, 6, 3, 6, 6. So these are all possibilities when I'm rolling two dice simultaneously. And the total number of sample points you can see here, 36 sample points are here. And find the event A that the sum of the dots on the two dice equal to 7. Means you have to find the event A, means which includes the sample points, and here the sample points having the pair of the outcomes of the two dice, means A is the outcome of first dice and B is the outcome of second dice. So it will be the pair of A and B. So, and it will be such that A and B, mean A plus B is equal to 7. This means sum on the two dice is equal to 7. So from this you can see that the event A will be corresponds to 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. And you can see that the sum of the dots on the two dice will be 7 here. For this it is 7. Sum of these two is also 7. Sum of these two is also 7, 7, 7, and 7. Now the same question, find the event B that the sum of the dots on the two dice is greater than 10. So you have to find the event B which includes the sample points and which is having the pair of A and B, and such that A plus B greater than 10 means the sum of the two dice is greater than 10. So it will be 5, 6, 6, 5, 6, 6. And another is find the event C that the sum of the dots on the two dice is greater than 12. So here C will having the sample points which is pair of A and B such that A plus B greater than 12. So, and because there is no such pair that the sum of the dots on the two dice is greater than 12, so there will be null set. So the event C will have the null set 5. Let us take one other example. An automobile dealer offers vehicles with the following options: with or without automatic transmission, with or without air conditioning, with one of two choice of stereo system, and the fourth one is with one of three exterior color. If the sample space consists of the set of all possible vehicles type, is combination of these, and what is the number of outcomes in the sample space? You can see there are two possibility in the second, and two possibility in the third, and three possibility in the fourth one. So the sample points, number of sample points will be 2 into 2 into 2 into 3, 24 sample points will be there, or you can say 24 different set of possibility of vehicle types. So the possibility of different vehicle types is 24 here. Now consider another example. Consider an experiment of drawing two cards at random from a bag containing 4 cards marked with integer 1 to 4. First point, find the sample space of the experiment if the first card is replaced before the second is drawn. So we have replaced the first card before the second drawn. So sample space, it will be 1 1. 1 1 here is because I am drawing a card and it is 1, and I am replacing this. So I can get again the card first also. So it will be 1 1 1 2 1 3 1 4, or 2 1 2 2 2 3 2 4, 3 1 3 2 3 3 3 4, 4 1 4 2 4 3 4 4. So you can see the total number of sample points here are 16 here. And the second part, the same question, and this time find the sample space of the experiment if the first card is not replaced. Now in this condition I am selecting a card but not replacing this card. So the sample space, it will be 1 2 because I have already selected the card first, so card first will not appear here. So 1 2 1 3 1 4, 2 1 2 3 2 4, 3 1 3 2 3 4, 4 1 4 2 4 3. And here you can see the total number of sample points are 12, and in the previous case when I am replacing the card, this was 16. So if the total number of cards are in very large number and the drawn cards are also in a large number, then finding the number of sample points in the sample space will be laborious and time consuming procedure. Fortunately, many clever tricks are available which save our time in doing this process, and the branch of mathematics which develop these is the combinatoric. We will discuss the combinatoric in the next lecture. So far, for the time being, this was lecture first of the lecture series of random processes, deduction and estimation. Till then, thanks for listening this lecture. Thank you.